Hello and welcome to 8.3 Pythagorean Theorem. We should be a little bit excited about this one because we've done Pythagorean Theorem before. You have done this probably in elementary school or middle school or both, and it was a theorem that was named after the ancient Greek mathematician Pythagoras. Okay, so the Pythagorean theorem is a squared plus b squared equals c squared. So you have to remember the important part that students forget sometimes is that a and b are the legs of a right triangle only. It doesn't work with a regular, any other kind of triangle, acute or obtuse. It only works with a right triangle. And A and B are the legs, where C is the hypotenuse. So another way to think of it is to think of it as leg squared plus leg squared is hypotenuse squared. Here's another illustration. This one is used quite commonly in proving the Pythagorean theorem. Let's just kind of break down what's happening here. I have a large square, and the sides of the large square are a plus b, okay, all the way around. And then I have another square inside where the side is c, and I have four little triangles, right? I have an a, b, c for all those triangles. So the area of the large square is a plus b squared, right? The area of the small square is c squared, and the area of all the triangles are half AB. So the area of the large square equals the area of the small square plus all four of those little triangles. So let's plug in all the formulas. So there's the area of the big square equals the area of the small square plus the four triangles. Now if I FOIL, or double distribution, of the a plus b squared, I get a squared plus 2ab plus b squared. Hopefully you can follow that. And then c squared will just stay c squared. And then if I simplify, 4 times 1/2 is like 4 divided by 2, which is 2. So I have 2ab. I'm going to simplify some more here. I'm going to subtract 2ab from both sides. And what does that leave me with? The Pythagorean theorem. So just another way of proving that it is true. The opposite of the Pythagorean theorem is also true, or the converse. So if you have the third side squared, you can subtract off a leg squared to get the other leg, right? So the sum of the squares of the lengths of two sides of the triangle equals the square of the length of the third side. Then it is a triangle, a right triangle. So if those things work, you have to remember that I could give you a picture that looks like a right triangle, but if the sides don't meet the Pythagorean theorem, then it really is not a right triangle. So sometimes you have to prove it the other way. Is this a right triangle based on these side lengths and hypotenuse? Okay, so let's talk about an equilateral triangle for a minute. This is where all sides are the same length and all angles are the same measure of 60 degrees. This is a shortcut because we can still do half base times height on an equilateral triangle for area, but what if we don't have the height? Or what if we only have one side? And so anyway, this would be a shortcut. It's the side squared times the square root 3 over 4. And it's very handy. You don't have to drop down the height and find the perpendicular and all of this. So if you just have a side, you can find the area of an equilateral. So let's practice that. This is a right triangle, right, that's in green. It's half the side, and I could plug in and use the Pythagorean theorem. Alright, so if I put the half s in there, because I have no idea what the actual number is, I didn't give one, I can still find the area. But do you see I need the height and I need at least the side. I need both things. But this is a proof that if I have a side, I can find the area. Here's another way. If I do half base times height, I have half, base is still s, and the height we said on the last slide was s square root 3 over 2. So look, if I simplify that, how beautiful it is. So here is an example that's in your book. If I just go ahead and plug 7 into my equation, I'm done. 49 over 4 can't be simplified, and square root 3 is a decimal, so we leave it just like that as an exact answer. Of course, on some of the homework I'll take decimals, but I need you to get used to exact answers. It's really important. So let's practice one more. This one is not in your textbook. It says a screen door measures 36 inches by 80 inches. Find the length of a diagonal brace for the screen door. So that means I would have a triangle. Here's my screen door, and here's my diagonal. Here's the dimensions that I know. So I'm going to have to make an assumption the screen door is a right angle there because it's probably a rectangle. Or, let's hope so. It's not a hobbit house. And I'm going to go ahead and square each side, and it should equal my diagonal squared. And then I have to take the square root of both sides. When you have to take the square root of both sides, it's okay to give me a decimal. I generally prefer to the hundredths place instead of to the tenths, like this example. Okay, so now it's time for your whisk summary. What I want you to do is draw a square of side S. That means you pick how big the square is. You want it to be a decent size because you're going to connect the midpoints of those sides to inscribe a second square in the first one. So if you make it like an inch, you're going to have a super tiny square inside. So I'd make it a little larger than that. Find the area of the inner square, and then I want you to make a prediction of if it was repeated. If you did that again to the little square, what would the area of that third square be? I need you to show all your work, show your picture, and no decimals. Alright, so I will see you in class.